So in section 4.2, we're going to discuss a lot of different things. We're going to discuss mutually exclusive events, the complement of an event, independent events, and calculating with the general addition rule, as well as the multiplication rule. So there's a lot of things going, but it's going to start with this example of taking the world and compressing it down to 100 people. So if you made this a village of 100 people, then the blood types that various people would have would roughly fall into these frequencies. So you've got your 100 people, 39 of them are going to have Rh positive blood. Think that Rh refers to the Reese's monkey factor. It's a protein that you can have on your blood. Most people have positive blood. Some people have negative blood. We're going to define a couple of events. A is going to be the event that a person chosen at random has type A blood, and likewise with B. And we'll also maybe do another example with Rh positive and Rh negative. But for starters, let's start out with the probability of A or B. How about if A or B? Now this is what's called a compound event, because it's more than just one thing that can happen. It's two things, probability of A or B. Now being kind of new to this calculation in this subject, we might start out by saying, well, let's do it as a probability of A plus probability of B. And in this case, you're actually right. You can actually calculate this probability this way. So let's look at the probability of A. Well, how many people were there that had type A blood in this table?
40.
40. Perfect. Now 40, though, by itself isn't a probability, right? Because remember, probabilities are between 0 and 1. But if you're trying to express this as a probability, it's 40 people out of how many total in this table?
100.
Good. So 40 over 100. Well, let's try probability of type B blood. So there's 10 people that had type B blood out of that 100 people. So we get a total of 50 over 100. Now, do I expect you to simplify? In general, no. This one might be just screaming out to be simplified. You get 1/2. So there's a 50% chance that if you just grab somebody at random, they're going to have either type A or type B blood. Nice, nice. But it gets a little more complicated than that. This is actually kind of a special example for reasons that I'll talk to you about in a minute. But let's do another one where I find the probability that somebody has Rh positive blood or type A blood. And if we do this one, something different is going to happen. And something that I hope grabs your attention. What's the probability that somebody has type Rh blood? Rh positive.
39.
Over 100?
86.
Okay.
86.
86.
I got 39 or 86. Which one of these should I use for Rh positive?
86.
86, yeah. All right, so 86 over 100. There's 86 people that have Rh positive blood out of the 100 that I have there. How about type A blood? Well, we did that just up above, so let me just copy that there. 126 over 100. Right now, you should be screaming out at me saying, wait a minute, wait. Didn't you tell us the other day that probabilities were between 0 and 1? And the answer is yes. So if you got an example or an answer like this on your exam, you should be saying, wait a minute, that's impossible. You can't have a probability more than 100% or less than 0. Those are the absolute bounds. Something will happen or it won't happen. There's nothing outside of that. So what went wrong here? How come I got something that's impossible? I just redid what I had up here.
Because it's double counting.
Ah,
Hmm.
nice insight.
Yeah.
Because as we total things up this way and then total things down this way, we double counted where they overlap. So if we subtract that overlap, we can fix this. So let's fix this, and we're going to fix it with something called the general addition rule. General addition rule. So let's see what that is and says. But the general addition rule is exactly for calculating stuff like this. And what we're going to do is we're going to take the probability of E or F, and these are some generic events. I just chose these letters because they're not already in use in our current example. And it's going to be the probability of E plus the probability of F, just like what we did before, except we're going to account for that double counting. We're going to subtract off where these overlap. And they overlap at P and probability of E and F. So you're subtracting off the double counting once, and that should do it for us. So let's revisit this now that I have this rule. So revisiting it, it's going to be probability of RH positive or A. Well, that's going to be probability of E, which in our case is probability of RH positive, plus the probability of A. So far it looks the same, minus the probability of RH positive and A. So let's see how that changes our calculation. Probability of RH positive, we already did that one. That was 86 over 100. Probability of A was 40 over 100. But now we got to envision and think about what the probability of RH positive and A. What's that? Well, it's going to have to be something over 100. But this is the people who have type A blood that is RH positive. How many of them are there in our table?
35.
I got to vote for 35.
Yep, 35.
All right. So people agree with Alec. Thank you. And now I get 91 over 100. So, okay. That looks pretty good. At least that's a valid probability now, right? At least it's something between 0 and 1. Whereas before, if you hand this in, you absolutely know with probability 1 that you've got one wrong, because you can't have something like this. And I'm hoping this is kind of like a little wake-up call for you. If you're like, wait a minute, I shouldn't get a probability that's negative. Oh, I shouldn't get a probability that's greater than 1. Those two kind of things should not happen. If it does happen to you, fix it. Okay. Doing all right on this one?
Yeah.
Let's stick with it for one more example. So we'll use that same data set, answer one more question like it. And let's see if I can get things all on the same screen. Close enough. Let's try and find the probability, for example, of RH negative or B. So another compound event, another application of the addition rule. So see if you can't figure out what to write down. I would suggest that what you do first is you rewrite the rule here for your particular letters. Now, it's my habit to always use letters or symbols that reflect the probability that we're trying to work with. B for type B, RH negative for, you know, again, the negative value or the absence of that protein. So can someone fill this in for me? What would that look like? Lydia? Can you fill in what this would be down here?
The probability of RH negative
RH negative, good, plus probability of what?
of B,
Mm-hmm.
being B, minus the probability of the blood type being both RH negative and B.
Perfect. Wouldn't change a thing. All right. So here's another look at that table. See if you can't finish filling in those probabilities. Thanks, Lydia.
Okay.
Okay. Someone help me out with these probabilities. Abdel, how about the first one here? What's the probability of RH negative?
14 over 100.
Perfect. 14 over 100. You want to do the rest of it?
Sure.
What's the probability of B?
B is 10 over 100.
And how many people have RH negative blood and type B blood?
2.
2. And overall, that gave us,
When you subtract that, you get 22. Yep.
perfect. Perfect. You guys comfortable with that one?
Mhm.
I have a quick question.
Yeah, please.
Right at the end of your top part, you have P, RH positive and B. Is it supposed to be negative?
I tried to make that.
Okay, just checking.
I tried to make it a, yeah, I tried to make it a negative, but yeah, it's a negative. Anything else? All right, let's keep going with an example that's on your handout from the other day. And let me pull that up for you here. No. Might help if I was in the right section. Still not the right one. There we go. All right, drive-through restaurants. So I'll give you a minute to copy this down into your notes while I do likewise. So with this data set, let's define a couple events. Event A is a person chosen at random, A to the restaurant A. Likewise, you have events B and events C and events D. I'll also use ACC as the event that a person chosen at random had their order prepared accurately. So let's calculate a few probabilities, starting with the first one, kind of outlined by the question over here. It says, if one order is selected, find the probability of getting food that is not from restaurant A. You know what? Tell you what, I'll go back and cover that one in a minute. Let's do one as a nice follow-up to the ones we've been working on so far. Probability of restaurant B, or that your order was filled accurately. So let's work on that one. Now you're going to use your general rule for this one. Probability of B plus probability of that your restaurant order was filled accurately. minus the probability of their intersection. We gotta remove that double counting. B and accurate. So let's see about some of these probabilities here. Starting with the first one, probability of B. So what's the probability that your order was filled accurately? Or excuse me, not filled accurately. What's the probability that you ate at restaurant B? We'll do accurately in a second.
Is it 325 over 1,134?
Yep. 325 over the total, which was 1134. Awesome. How many people got an order that was filled accurately?
989 over 1,134.
Yeah. So 989 divided by 1134. That's not entirely great. That's like, 13% of people go away without an accurate order. So not so hot there. And some of these look worse than the others, but let's keep going. Probability of B and accurate. So how many orders, what was the probability of getting an accurate order from restaurant B?
267.
Good. 267 out of the 1134. Perfect. And so altogether, that turns into 1,047 over 1134. Nice. So the thing with these is you've always got to go back and subtract off that double counting. But a good question might be, well, why didn't we have to do that with our very first example when we first looked at this kind of stuff? And the reason is that when we first looked at this kind of stuff, we had a special kind of example in terms of special events, and our events were mutually exclusive. So let me go back over here, see if we can't take a look at what mutually exclusive events are. So mutually exclusive events are pictured here. These are events that have no overlap. If one occurs, the other one can't. If you notice this with this Venn diagram on the right, you're either an A or you're not an A, okay? There's no overlap for events A and B. They can't both occur. But how about the Venn diagram on the left? Is there a way that event A and event B can occur at the same time? Yeah, it's that part where they overlap. So with events that are mutually exclusive, or sometimes I think the author seems to prefer disjoint. I like mutually exclusive because it's really telling you what's going on. It says one excludes the other. They can't both happen. The probability that something can't happen is what? What's the probability of something that can't happen?
0.
0. Thanks, Joe. It's 0. So in our very first example, way back when in this section that we did on this stuff, we calculated the probability of A or B just by adding up these two probabilities. What this rule seems to suggest is I needed to subtract off the probability of A and B. But you know what? There's no A and B. A, B, you might as well call that C or D or something like that. It's not A and B. It's just different. So there's no intersection here. So that term here, probability of A and B up here would be 0. That's why I didn't have to worry about it in our very first calculation. All right, so we've discussed mutually exclusive. That's good. That's good. Let's move on and look at the events here in a different way. Are we okay with what we've got so far here? So up till now, we've been working with just, one sample at a time from this table. I'm going to start taking 2 samples, sampling this twice, and see what happens then. So let me do this. Let's talk about what happens if I were to sample and get B1, or get somebody from the table who ate at restaurant B with my first sample, and then sample again and see what happens with the second person. So I'm going to write down some more notation here for us. And we're going to consider different types of probabilities. B1 is the event the first person chosen person chosen, and it's at random, ate at restaurant B. And then likewise, I'm going to let B2 be a similar event, the second person chosen ate at B. Now we're going to calculate a different probability, and we're going to calculate it 2 different ways, or under 2 different circumstances. I could ask you to find the probability of B1 and B2. In other words, I'm asking you to find the probability that we can pull 2 people in a row out of this table at random that ate at restaurant B. And let's see what that probability turns out as. So now I said we're going to do that in 2 different ways, and we are. We're going to do it first with replacement. And second, without replacement. Now, with replacement, it's kind of odd and maybe doesn't seem like the right way to work on these things. But with replacement means what we're going to do is we're going to take somebody from this table at random, take a look at where they ate, and then put them back in the mix, and then pull out another one. So by putting them back in the mix, we could actually pull out that person twice. But it doesn't matter. We're putting them back in the mix to pull out a second time. So that possibility exists. Now we're going to end up with a product of 2 fractions. So for the first one, I want to figure out, well, what's the probability of pulling somebody out of this table that ate at restaurant B? What's the probability?
325 out of 1134.
Thanks, Joe. 325 out of 1124. 1134, my bad. Now, oddly enough, with sampling with replacement, what you're going to do is you're going to look at that person, say, okay, they ate at restaurant B, and I'm going to throw them back into the pond, let them swim around, mix up again, and pull out another one. What's the probability that the second person ate at restaurant B? And don't think too hard on this one, because it's not supposed to be hard.
Wouldn't it just be the same odds, 325 over 1134?
Yep, same odds. 325 over 1134. Great. Now, if you really wanted to, you could write that as something squared, and that's fine. 325 over 1134 squared. That's great. But what I really want to get to is this part over here. What if we did that same experiment except without replacement? We're not going to put them back in the pool to sample again. Now that's not going to affect things on the first draw. On the first draw, it's still going to be 325 out of 1134. But if I don't put that person back into my table, what are the odds of getting somebody, or what's the chance of getting somebody on the second draw that went to restaurant B?
324 out of
324.
1134.
Close.
Would it be
324 over 11.
33.
33, okay.
33, yeah. So you're reducing the numerator and denominator because you're taking one out of each. You took one out of the overall pool, and that one happened to be somebody who ate at restaurant B. So notice that it changed here, and it didn't change here. And that says something special about events B1 and B2. So let's understand what that says. B1 and B2 are independent events. What happened with B1 didn't affect the probability of B2, right? They're both the same. Now over here, things are different. B1 and B2 are dependent events. If you're not independent, you're dependent. And the reason we have dependent and independent is because of the method of sampling that we chose. Sampling with replacement leads to independent events. Sampling without replacement leads to dependent events. Okay. I'll give you a second to copy that down, and then I'll show you in the book what dependent events looks like, how it's defined. I'll tell them I'm busy. I'll call them back later. All right. All right, so we got that one. Can I flip over to a definition for us real quick?
Wait, so why did you take away one from the replacement without the replacement?
All right, so the reason we took away the one was because we're not sampling without replacement. So after we took this person out, there's one less person in the table. So there's one less person who ate at restaurant B, and there's one less person overall. So that's why you took one out of the numerator and denominator. It's because you're saying, okay, on the first draw, I got somebody from that ate at restaurant B. But now there's one less person because I already took that person out of the pool. So there's one less that ate at restaurant B, and there's one less overall because that person's gone. You're sampling without replacement. Whereas over here, after I took that person out, said, okay, great. I put them back in the pool, shuffled up, and drew again. So you could pick them again. And essentially what that means is that the probability for the first draw and the second draw are the same. So that's why they're independent, is because whatever happened on the first event didn't affect the probability of the second one. That's not true over here. What happened on the first one, we got somebody at a restaurant B, affected the probability of what happened at probability of the second person eating at restaurant B. It's not a big change. And in fact, a lot of times we'll just kind of pretend that change doesn't exist, but it is a change. So they're dependent events. Now, before I go on? Have I kind of helped out your concern on that one?
Yeah, so what you're saying is whenever we get the without replacement, will we subtract one every time or is just
Yes. So let me ask you a kind of a follow-up question. If I picked a third person out of this pool, again without replacement, what would the next probability be? Can you guess?
would it be 321 to 1130?
No, I'm just picking one more. So this is the first one. This is the second one. The third one would be, and I think you got the right idea. It's just the third one would be 323 over 1132. You'd be subtracting one again from the numerator and denominator.
Oh, okay. I get it now.
Yeah, but I think you got it overall. So that's good. Now, coming back over here, here's the definition for independence. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. So, and you can have several events that are independent as well. If A and B are not independent, they're said to be dependent. And so that's what we saw going on here. The fact that we pulled out somebody that ate at restaurant B here didn't change the probability that we could get the second person that ate at restaurant B. Those are the same. But when you're sampling without replacement, it did make a difference. All right. Let's take a look at another one from the book. Any questions on this much so far? We're covering a lot of ground. I get it. Let's keep going with an example on page 157 of the book.
Can you go back to the Venn diagram for like a second? I wasn't sure if I understood that part with the mutually exclusive.
Sure. How come this isn't moving? Rules, probability. There you go. So there's your Venn diagram. Mutually exclusive means they can't both happen at the same time. So it means there's no overlap from one to the next. One excludes the other is kind of the way you could read this. Mutually exclusive. They each exclude each other. If this happens, that can't. You know, if you vote for a Democrat, you can't vote for a Republican, you know, for the same office. I mean, certainly you can mix your ticket, but, you know, you've got one vote. You've got a choice. It's heads or tails. It's not both. Male or female, not both. Not trying to get into any crazy discussions there. So there's a lot of things that are mutually exclusive. So if one happens, the other one can't happen.
Okay, thank you.
All right. So let me go back to page 157. And they do something here in the book that I wouldn't do to you on an exam. And that is they kind of make you come up with your own table. But let's work with this a little bit and see if we can't at least get through this example. See what they did and see how to create your own table so that if you run into a question like this in the homework that you can do this. The one panel THC test for marijuana use, which is provided by the company Drug Test Success. All right, so here's the numbers. Amongst 143 subjects with positive test results, there are 24 false positives and 150 and amongst 157 negative results, there are 3 false negative results. So, wow. So we need to construct a table for all this. And let me help you out here. So we'll write negative test and a positive test. and then uses marijuana and doesn't use. Let's draw ourselves some boxes here so we can fill those in. Okay. So they said there was 143 positive tests. Let's just double check that. Yeah. So amongst 143 subjects with positive tests, there are 24 false positive results. So what they're telling us is this marginal total, that's 143. But 24 of them are false positives. So where should I put that 24? Up top or down below?
Below.
Yeah, down below, this is where you're going to find the false positives. Is because there's some people that don't use, they're going to get flagged for having that result. So, okay. Now, what's that leave for up here? Or how would I find what's left up here?
Subtract 24 from 123, leaving 119.
Perfect. Thanks, Joe. You can get this one by subtraction. Now, flipping things over, there was 157 who had a negative test, and of those, there was 3 false negatives. So where does that 3 go? Up top or down below?
Up top.
Up top. Good. False negative means that you use it, but that's nah, you don't use it. All right. I kind of wonder if he's going to change this in the 14th edition because marijuana is legal in a lot of states now. So we'll see. In any case, what's that leave here? Somebody I haven't heard from today. What's going to go in this last cell?
154.
Thank you. 154. Beautiful. Let's develop some notation for some of these events. P1 is the event. The first person chosen at random. At random has a positive result. Or positive test. And then P2 is going to be the event that the second person chosen at random also has a positive test. Let's calculate some probabilities under the same circumstances that we just had. All right, so changing things up. We're going to find probability of P1 and P2. And kind of like our last example, we'll do it sampling with replacement and sampling without replacement. So A, sampling with replacement. and B without replacement. Okay. Let's pull those together a little bit. So what's the probability of getting first one, then the other that tested positive? Let's start with the first one. What's the probability that the first person tests positive? Ooh, I should probably put some marginal totals in here. That would be 300 here, and that'd be 178 and 122. There you go. That's nice.
Would it, for positive test, would it be 143 over 300?
Thank you. 143 over 300. Now that's for the first one. If you're sampling with replacement, what's the second one going to be?
Same thing.
The same
Same
thing.
thing. Yep, 143 over 300. Or basically 143 over 300 squared. Okay. All right. Let's work on sampling without replacement. So without a replacement, the first choice still is 143 over 300. Someone I haven't heard from yet today want to give this one a shot? What's the probability that you've already taken one out and you get another one who had a positive test? What's that probability going to be?
142
over 299.
Thank you both. 142 over 299. Nice. And that's not going to simplify at all. So just leave it like that. I really don't care about lowest terms in this case. All I care about is the right number. So are we okay on those two?
Yep.
Yeah.
All right. Now, perhaps I shouldn't have used the notation of P here because P is probability and it's also part of our, it just gets a little bit messy. So what I could have done was done something a little bit different. For instance, instead of looking at a positive test, I could let N be the event that someone tests negative. A person tested negative. Now, if that's the event N, what's the event N bar going to mean? Remember this
Any
one?
other result that's not positive, negative.
Yeah. And in this example, if you're not negative, what are you?
Positive.
Person tested positive. And there's something interesting that happens with complementary events, or the event of a complement, the probability of a complement, I should say. And let's look at that real quick to kind of finish things up here for this section. It's actually not as finished as I want, but we'll add some more to it later. So right here, here's the rule of complementary events. Now, with our current example, if we were thinking not of A and A bar, if we were thinking of N and N bar, with our current example, it'd be saying, okay, the probability somebody tested negative plus the probability that somebody tested positive is 1. Because basically you've got everything, right? I mean, in this table, you tested negative or you tested positive. That's it. There's no other choices. So when you add up those two probabilities, you're going to get the same thing. Let's actually take a quick kind of look at that. Let's see. This way. So probability of a positive result. No, let's see. Probability of a negative result plus probability of a positive result. What's the probability that you got a negative result here? $157 out of 300. 157 out of 300. And the probability that you get a positive result is 143 over 300, which is 300 over 300, or 1. Now, an interesting thing you can do with these kinds of results is you can calculate things indirectly. What do I mean by that? Well, these are your rules of complements. For instance, the probability of n, probability of a negative result is 1 minus the probability of a positive result. So it'd be 1 minus, let's see, the probability of a positive result was 143 over 300. Instead of writing a 1 here, I'm going to write 300 over 300. That way I can subtract them. And when I do that, then I end up with 157 over 300. Yay. So that's the probability of a negative result. And you get that indirectly. Now, this idea of using the rule of complements is okay to look at in this section, but it's almost vital in the next section, section 4.3. But we'll stop with things here. Any questions or wrap up here? Anything else on what we've covered here? Okay, let me stop things here.